All right, so let's get going. All right, so only a few classes left. As a reminder, quiz this week. And you got to know metathesis mechanism, and you're all going to get a semi-challenging metathesis mechanism question where you're going to have to sort of use a little bit of problem-solving skills, and certainly you're responsible for knowing all of the reactions that are in the sort of the amine chapter, as well as the sort of carbon-carbon bond forming chapter, even those that we didn't necessarily talk about last class, as I said last class. So, so today, as last class, we focused on metathesis. So again, you're not going to be responsible for, on the quiz, as I said, you're not going to be responsible for the mechanism of Suzuki's, Still's, these palladium-catalyzed cross-couplings, but you do need to know them. And you should expect to get a question on what is the product from this reaction, or what are the reagents necessary to carry out this transformation using the palladium-catalyzed cross-coupling. So if somebody sort of asked me, am I responsible for knowing these mechanisms for final? Well, when you don't get a chance to cover something, and the last chance to test you on it is the final, I'm going to spend a whole day on mechanisms. You could probably plan on getting a palladium-catalyzed cross-coupling mechanism on the final. So this is where a lot of this is going to come down. So as I sort of stated yesterday, and I'll just sort of reiterate, I think it's often nice to start this chemistry describing cross-couplings of the variety of, as your book describes, Still's and Suzuki cross-couplings, whereby you have an alkyl whereby you have an alkyl halide, and then you have an alkyl metal, and for the sake of the book, what we're talking about, but these metals are sort of borons, so boronic acids, or tins. These are the ones that your book emphasizes, and these are the two most widely used. But there's other things like Grignards, for example, are a class of cross-couplings as well. But again, for your sake, know the tins, recognize the tin and the boronic acids, as those are, again, the most commonly used, and those are the ones that your book focuses on. And when you take these two and you mix them in the presence of a palladium source, and again, whether it starts as palladium 0 or not, generally the mechanism for these transformations is best thought of starting from palladium 0, as I'll sort of reiterate in a second. And the net result is you get a R1, R2, R1, R2. You get a carbon-carbon bond forming reaction. And as we said last week, the mechanism of this is catalytic in palladium 0, so this is the catalyst. And we can use this as the first mechanism of this type, and then we'll sort of show where the parallels are to the others. And so the catalytic cycle is often based around the palladium. And so what's happening through the catalyst cycle is that you're going to be sort of changing the nature of the palladium source between palladium 0 and palladium 2. And so it's oftentimes, when we're doing catalytic cycles, it's the palladium that's the catalyst, so we're going to sort of focus on what the palladium is doing, and then it's going to be regenerated. What's going to happen in the catalytic cycle here, palladium 0. As the first step is that the palladium, as we sort of stated last week, it's going to insert into the alkyl halide. And so you guys haven't seen this quite yet, but you kind of have. I think the good parallel to this is a Grignard reaction, right? You took magnesium 0, you treat it with an alkyl bromide, and you generated the Grignard, right? And so the magnesium ends up kind of in a way inserting itself between the carbon and the bromide, but usually we think about it as an ionic now interaction. At this point, we'll think about it more as the complex, but what's going to happen is the R1 bromide, the palladium is going to insert itself into there. When this happens, the palladium is now going to be giving up two of electrons. You can sort of think about it as it's got these two electrons. It's now going to take two of these electrons and use them to make bonds with the alkyl group here and the bromide. Okay, this is why we sort of consider it, again, I don't want to get too deep into sort of transition metal electron counting, but needless to say, this doesn't have any bonds to it. Now it's got two bonds. That's part of how we do the counting, is when you start having these metal covalent bonds, we start talking about the oxidation state at the palladium. So in this case, it owns all of its electrons. In this case, it's using two of those electrons to share to create two new bonds, right? So this is a net neutral process. So again, if you want to take an organometallic course, you can get more in depth about this. But for this standpoint, just recognize that that insertion leads to a palladium-2. Okay. This next step, you know, I've asked people that are in the know about this in terms of the best way to think about this, and certainly the best way to think about the mechanism here. But it's the transmetallation. You'll get a lot of different ways in which people sort of think about how this transmetallation will take place. Now, the metal, okay, one of the ways in which we can think about it is, I think the way that, I believe the way that your book sort of states it, but this, I don't like it this way. It's sort of a 2 + 2-ish type process, where you're sort of making this bond, sort of a 2 + 2, almost like the metathesis. I think the way that's probably more rational for you guys to think about it, though, is sort of nucleophilic attack at the palladium, and this will come up based upon, you know, this will come up a little bit with some of the acetate work that we're going to get to in a second. But I think that the best way to maybe think about it is that, you know, you're going to have these metal carbon bonds. These are often referred to, if you talk to people, again, I always bring up Mark Biscoe because he's somebody in CUNY that sort of works on this chemistry, but Mark will often call this the electrophile, this the nucleophile. Well, if this is your nucleophile, how would it behave as a nucleophile? Well, you can imagine that carbon attacking, kicking out the bromide. Now, however you want to sort of think about that, the net result is going to be that you're going to have the metal, whether it's this tin or the bornate, that's going to end up with the bromide. And then what you're going to have is your sort of now palladium, which is still a 2, right? You still have the 2 covalent bonds. Now instead of it having a halogen on it, it's going to have that other alkyl group. And the final step is going to be the regeneration of the palladium-0. So we're going to do a process that's called a sort of a reductive elimination. Okay, so what's going to happen here is we're going to generate our carbon-carbon bond, and through that process, we're going to regenerate palladium-0. Okay, now you have palladium-0 again, which can then insert into the alkyl halide. You can then undergo the transmetallation, and then you can do the reductive elimination. And so, really, in this case, it's 3 steps. And so I'll just give you guys the names for them. This first step, so again, remember oil rig, right? Oxidation is loss, reduction is gain. So oxidation is loss. So this is the first step is an oxidative insertion. Is what this first step is called. If you think about what that name is applying, it's applying that you are inserting the palladium into the alkyl halogen bond. So it's an insertion. The process is an oxidative insertion because the palladium is getting oxidized in a way, or it's losing 2 of its electrons right through that process. This step here is called a transmetallation. Right? You're going to take your boronate or your tin or your Grignard or your, you know, other metals that we might have in this, and we're going to get a transmetallation where the palladium is basically exchanging. These sort of metals are transmetallating, so you're exchanging what's on what. So now the palladium has this R group, and now this metal has the bromide. So again, it's transmetallation. You're exchanging, the metals are exchanging what they have. And the final step is a reductive elimination. Okay, so when we think about what an elimination is in general, we're sort of basically, going from maybe one molecule to two molecules, right? Say, for example, if we're going to eliminate, if we're going to do an elimination of a halogen, right? We're going from an alkyl bromide to, say, for example, an alkene and HBr or something like that. So similar type of thing here. We're going from one molecule to two, and the process is reductive again because now we're gaining electrons. It's going from sharing two of those in a way to now sort of owning those electrons. At least that's the way that we can think about it. It's at least consistent with what we saw before. Okay, so this is the standard cross-coupling, and if you think, and you look in your book, what this, at least in terms of the chemistry that's discussed in your book, this is the mechanism for both sort of Stille, and so the Stille cross-coupling is, who knows, tin, right? So Stille is tin-based. And the other one is Suzuki. And this is going to be boron. Okay, and these are the two that your book discusses. But again, there's many, many, many other variations of these that you can do. These are just the two that are most widely used in the literature, in large part because these are stable-based tin molecules. Now, one quick thing about the that I think is worth sort of describing these two maybe before we move on, because there are some differences between sort of Stille's and Suzuki's that are worth mentioning. And they come down to this transmetallation step that we've seen right there. Okay, and so if we have a, let me turn off the board space here. So if R1, I guess it's R2, is tin, usually the tin has a few alkyl groups to it. Okay, so these alkyl groups, your book might say tributyl or trimethyl. Tributyl is usually the most, and so I figure that I'll just sort of answer a few questions that I think one would have, right? We have a tin here that has 4 carbons bonded to it. And as you'll notice, in principle, if this is the tin, right? In principle, you can get any of those. You could also potentially get transmetallation where you form the carbon-carbon bond with the butyl group, right? So that the R1, the R2 is not the R2 that we wanted it to be, but for example, the butyl. And you might ask, well, why doesn't that happen? And the truth of the matter is sometimes that does happen. Sometimes you'll try to run a Stille reaction and you'll end up getting the butyl on there. You had that problem, right, Mike? Or was it the methyl? This is the methyl. So another common one you'll see is trimethyl. And so Mike, oh, by the way, Mike, who has Mike for recitation? All right. So I want to see all you guys on Wednesday because Mike is defending his thesis on Wednesday. So there'll be things around. He's going to be giving a talk. I urge as many of you as possible, and even if you're not in his recitation, show up to Mike's thesis defense. He won't be talking about that because he did many other things that ended up working, so he won't be talking about how the methyl gave him problems. But you do have these issues where, the transmetallation could be other carbons. And so it just turns out that, by and large, most of what you see for Stille cross-couplings, there's a preference, and it turns out that an sp2 hybridized, so these would all be sp3 hybridized carbons. Usually what you're talking about is R2 being an sp2 hybridized carbon, or even an sp, I can't think of any sp examples in my head where it's an sp10, but usually what we're talking about is sp2, so aryl tins alkene-based tins. And it turns out that those transmetallate from those carbons much more efficiently than an sp3. Mike's issue, when he had the methyl group, it turns out that I think the methyl was also giving him problems. Again, you have 3 methyls versus the 1, so stoichiometrically you're up against a little bit of a wall there. It's also smaller, and so maybe getting into the right geometry might facilitate doing that as well. Apparently butyl's even slower then. But again, don't worry too much about that, but I think that's a fair question that many of you might have. Well, why doesn't the butyl group? And the answer is sometimes it does. And so you're sort of relying upon some of these differences. And one of the ways that you might be able to rationalize this is based upon kind of how we talked about. Again, this isn't exactly how it works, but I think from a rationalizing it standpoint, you can sort of think about this as being, as we sort of said, we could think about maybe based upon this mechanism that I mentioned, right, you can imagine that having the negative charge and that having the sort of positive charge. And so what's going to take on a greater negative charge? An sp2 or an sp3? sp2, right? So sp2 carries negative charges stronger than sp3s, and so this is at least one way that you can rationalize them. It's also a way that you can rationalize the nucleophilic character of these molecules. Now, what's interesting about this is that we might be able to draw this, and certainly maybe the tin is stabilized by having all these alkyl groups around it and being a big atom. But that might be a weird way to think about maybe boron. Right? So usually what we're referring to with boron is sort of boronic acids, such as the one that I've shown here. And certainly if we took this molecule and we imagined the same thing, right? I mean, boron is electronically poor, right? It sort of wants to take on electrons, right? It already only has 6 electrons to it. It oftentimes likes to take on negative charges to it. And so this would just be a disaster, right? If you were to think about this from the standpoint of now you've got even less, right? That's just horrible, right? You're going from a molecule that already doesn't have a full octet, now you're pulling 2 additional electrons out of it. And so one of the big differences between doing this, and so as you might imagine, this doesn't work. Like, you need to activate the boronate in order to get this to work, yeah?
Isn't it an aqueous solution?
Yeah, so right, so what you'll find, and this is sort of, Jonathan sort of just got at the point. Tin, one of the big differences between these is tin, you can actually, and you're generally running this in sort of, a non-aqueous solution. So you're usually running it in like THF or DMSO. I'm trying to think of some of the other cross-coupling solvents. But by and large, usually when you run Suzuki cross-couplings, as sort of Jonathan said, it's oftentimes in an aqueous solution. It doesn't need to be, but it's very often run in an aqueous solution. And that means that this isn't what you have. What you have is really this, right? What you have is sort of the negatively charged boron, and that becomes a little bit maybe easier to see this. And so what you need to do is you need to sort of activate that boron in some way to do this. And so if you're not going to use an aqueous solution, there are methods that you can potentially use where you have some, for example, organic soluble coordinator that can activate it. But anyway, so this is one of the big differences, is that the vast majority of Suzukis are run with, when you see them in the literature, they're run in an aqueous environment, and this is the reason why, is that you need to make that sort of more nucleophilic, if you will. Okay, so that's one of the big differences. Another difference, though, on the reverse side, so that's why this would be a little bit more difficult, right, that you need to activate this. So then if you need to activate this, why do people like these rather than these? Well, tin, it's really genetics is the real reason why I'm going bald, and I am bald, but tin is also highly toxic as well, and so people will often like to avoid using stoichiometric amounts of a tin reagent, particularly the tin halides that you ultimately generate. Those are fairly toxic, and one of the potential sort of side effects of tins is hair loss. So So this is a little bit of info on these guys. Okay, so any questions about Stille Suzuki? Okay, all right. Okay, so oxidative insertion, transmetallation, reductive elimination. Remember those steps. Okay. All right, so let's discuss some of the other cross couplings that we have.
Reductive elimination, is it bend shape or you don't know?
So you
Drive it forward.
Does it have to be bent shape? I mean, I drew it in that way so it's easier to see. But yeah, you do need to get those.
Is it or not? Oh, we don't know.
I'm pretty sure it is. I don't remember the exact geometry at the site. Do you know the geometry? It's.
They will have to be the same place because your bond forming is a brace apart.
Right.
It's like
Well, they definitely need to be. Yeah, they definitely need to be near each other. Not sure what the angle is, but
It can't be like 20 feet.
exactly. So it's so the way that I drew it is perhaps closer to what it is, but we're not really discussing geometry at the Palladium right now. But obviously that's really important for these. It's just sort of beyond the scope
Oh,
of
yeah,
this
just
class.
ask what drives it to form. What drives it out?
What drives it? Thermodynamically, that's a good question. I think, what is the thermodynamic driving force behind this? I don't know. Yeah, I don't know off the top of my head. It could be the.
It's really developing. Like the bond is more stable than the palladium one. So the carbon-carbon bond is really more stable than the palladium.
So that's what's going to drive the reductive elimination.
I guess so. That would be my guess.
Right, but yeah, I don't know. Look into it.
Take over the break. Take over.
So Anton volunteered to come and tell us what drives it next time. But I don't know. But it's a good question. I don't have the answer right now. All right, so. All right, so here's another reaction. This is the one that your book starts, and actually, in terms of historical perspective, this is one of the first reactions that was developed for cross couplings. And so this is a Heck reaction. And so mechanistically, I think it's a little bit more. So I like to teach the other one first because it's mechanistically, I think, a little bit simpler. But just historically speaking, your book describes the Heck first, and also historically speaking, this is one of the first cross couplings. I think it was the first that was actually learned. So in a Heck reaction, usually you have triethylamine or some base in this as well, is that you're making alkenes. I'll draw it as trans, although sometimes it can be different based upon specific examples. But as we'll see, the chemistry of the Heck has some similarities to what we saw previously. And so if you were to go ahead and guess what the first step to this mechanism would be, you guys could probably all guess based upon what I've shown you, right? Kirill's nodding his head. And I don't know if that's because he does research in an organometallic lab or what, but first step.
We don't work with
Right.
exudative insertion.
Right, so exactly. So the first step is going to be, we're going to insert just as we did before. So our alkyl halide, this is going to be a fairly common theme from these. The first step is going to be the alkyl halide is going to insert into this. Right? This is how we're going to have now palladium-2, okay? And one of the differences now is that we don't have the metal there. And so what we need to do is we're going to draw some mechanisms here so that we do ultimately get, because where we want to get, right, is we got to make this bond, and that bond is likely going to come through a reductive elimination to sort of make the carbon-carbon bond. So the question sort of becomes, how do we get the palladium with the 2 carbons on it? And the way that this works is, I'm trying to think which direction we want to go. You're basically going to get the alkene is ultimately going to coordinate which way we go here. The palladium is ultimately going to coordinate to the alkene, and so this is sort of a dative bond, so it sort of becomes a ligand for the palladium. And the importance of that is it's sort of going to bring it close by. And then what's going to happen here is that you're going to get sort of oh wait, hold on, I have it wrong. Give me a second. Yeah, girl.
How do you determine regency? Is it sterically driven?
So oftentimes these are sterically driven, but not always the case. If, say, for example, it's an intermolecular, sometimes it can be based upon ring strain and so forth. So all these factors could come into play. But okay, so the palladium's going to insert, and what's going to happen here is we're going to do a similar type of sigma, sort of a similar 2+2 rearrangement. And this is how we're ultimately going to make the carbon-carbon bond. So in this case, it's a little bit different because the reductive elimination is not necessarily the carbon-carbon bond forming event. It's this 2+2. Okay? And so we're still at palladium 2, but by sort of coordination in this 2+2, this is how we're going to make this carbon-carbon bond, and we're going to keep that palladium on it. So that's the first difference, right? So we're doing the same insertion, but now we got to do a 2+2 that's maybe a little bit more reminiscent of the metathesis reaction that we saw. And now what's going to happen is, so that's the carbon-carbon bond forming step. The tricky part is a new reaction that we're going to see next. So there's sort of two new reactions. So the first is this 2+2. The other is that we actually are now going to eliminate the palladium through a, through a reaction called a beta hydride elimination. Okay, so this would be the alpha hydrogen, this is the beta to the palladium. So palladium, alpha carbon, the beta hydride, okay, is going to generate our alkene. Now, the stereochemistry here, you can get into the stereochemistry here if you'd like, but ultimately what you need for this elimination to take place is you notice it's kind of a syn elimination like we saw previously. So the palladium and the hydrogen have to be syn with one another in order for this to take place. Now, if you're given two options, chances are it's more likely to go with the trans for similar reasons to what we brought up with the Cope elimination, right? How to get those syn to one another, have the R groups as far away from one another in the elimination. So it's a similar type of thing. So given the option, you're going to have trans, yeah. Thank you. And so you're going to end up getting the double bond through that elimination process. But generally, you can get trans, but sometimes you might get a little bit of cis depending upon what's taking place. In addition, if you don't necessarily have, say, for example, if there's only one hydrogen or something like that, then maybe other features could come involved. But the question here is you notice that we're still at palladium 2. And what we need to do is we need to get back down to palladium 0. And again, if you sort of notice that in this case you have a base that's around, and the importance of that base is there's a couple different ways that we can do this mechanism. We can do now a further reductive elimination to generate HBr, which will then be soaked up by the triethylamine. Or you can just use the triethylamine here, however you want to have the mechanism. I often like to draw it this way. But you can do a similar reductive elimination. What you can do, in addition to this, either one is fine. You can do a sort of a reductive elimination similar to how we did previously with the carbon-carbons, generating HBr, and then HBr is going to react with the base. But ultimately, as you can sort of see, you're generating, unlike the previous case where you generated a metal halogen, in this case, you're generating HBr, or, depending upon what the insertion is, it could be HCl, or it could be HI, or it could be triplet acid, or something like that. So you need the sort of base in there to help scavenge that, or promote the sort of reduction of the palladium 2 to 0. Hi.
If you had HBr, wouldn't that ruin your R2?
Right, well that's why, so, say it again? Oh, are you saying HBr? Well, that's why you wouldn't want to be allowing to generate HBr, right? HBr, you probably, there's very few reactions where you'd be okay using HBr and having HBr around, unless your intention is to actually have the HBr to do what HBr does. Yes, exactly. So either of those mechanisms is fine. You can either do reductive elimination. I like to have it just sort of eliminate it itself. Okay? Okay, so this is the Heck reaction. Oxidative insertion. Okay, then you get a sort of a sigma metathesis, or however you want to sort of get it, this kind of 2 + 2. It's the 2 + 2 that ultimately makes the carbon-carbon bond. Now, the challenge here, and you notice that I almost made the mistake early on, you're going to coordinate and you're going to make the carbon-carbon bond through this 2 + 2. I almost made the mistake of making the carbon-bromine bond early on. So this is just, you have to recognize that there's two bonds that you can do this. The one that will eventually lead there is the one that's going to make the carbon-carbon bond. Okay, so that's what you have to remember. Okay. All right, so this is one of the other coupling reactions. This is the Heck reaction. All right, clear? As much as we can be at this point, right? So, all right, so another reaction that involves palladium that we'll often see in alkenes. I don't know if the book gives it a name, but Barry Trost has done a lot of work on this. But it's from allyl acetates. And so here's just an important thing about So previously, what we saw was that most of the insertion took place with, carbon-bromine bonds, and so you had this sort of oxidative insertion into that group. It turns out that when you have, so you guys remember the term allylic, right? So when you have sort of an alkene and then a CH2, this is sort of called an allyl group, right? And so this molecule that I have here is actually allyl acetate. And as you guys know, an acetate group isn't necessarily one of these molecules that we often view as a good leaving group, right? It's say for example, acetic acid, the counterion to acetic acid, compared to like some of these others that we've seen are worlds apart, right? An acetate's pK is somewhere around 3 to 5. Bromide, chloride, triflate. I mean, we're talking about -8 and even lower, right? So an acetate isn't necessarily a group that we'll often think about as a leaving group. And so if you were to take this and treat this with, say, for example, the nucleophile the book uses is a sort of the malonate electrophile. I think this is the example that the book gives. So if you went ahead and treated this molecule with this sort of alcohol, sort of enolate type chemistry, right? So we have this enolate, and we're going to try to treat this with this acetate. It's probably not going to react, right? And it's certainly not how you might want it. But it turns out that for allyl acetates, you can actually promote these transformations using palladium catalysts. And so if you use a palladium catalyst in this transformation, you can actually, I'll just abbreviate these as CO2Me. You can actually make that carbon-carbon bond previously. And so allylacetates are fairly useful in palladium catalyzed cross couplings. Okay, so what makes a palladium? So I sort of said earlier, the insertion of a carbon acetate bond is not the greatest, but as it turns out, there's a slight difference to an allyl group, and part of the reason behind this is that when you do the insertion, mechanistically it's perhaps a little bit different, but it's best observed. I'll go ahead and just do it related to what we saw before and then draw the form that actually okay, so this would be the sort of the standard reductive elimination, and this isn't necessarily going to happen. Certainly isn't going to happen if you don't have the allyl group there. One of the things that's special about an allyl palladium acetate, and you'll see this in the book, it discusses it a little bit, but it has to do, previously you saw with the Hectus alkene. But as it turns out that when you have this palladium acetate, there are resonance forms of this that help further stabilize this palladium-2 species. And some of the ways that we could sort of think about this are, I'm just going to put a dot there so that we can keep track of what's going on because there is symmetry here. But as it turns out, this palladium has a resonance form where you can basically walk this palladium over to the other side of this carbon. Okay, so this carbon, basically the carbon-carbon bond that we have here, right, becomes a double bond. This carbon-carbon bond that we have here becomes a single bond, and the acetate ends up over in this direction. Okay, so how does this happen? Well, one of the things that your book sort of illustrates is that you can have species that look something like, you know, if you have the palladium inserted, you can start to get a little bit of a bonding to this position. Hold on one second. And so you can imagine a mechanism that looks, for example, something like that. Yeah, Jonathan, go ahead.
Did you forget the palladium?
Oh my God.
Yes.
Thank you. Monday. All right, so, sorry about that. So yes, it's the palladium 2. Okay, and so one of the ways you can imagine that is that the palladium sort of coordinates to the alkene, and you sort of get this rearrangement that I've shown you here. The way that I think is sort of, I guess, better, or at least certainly the way that I think about this more, is if you envision a allyl anion, such as the one that I'm showing you there, right? You recognize that that has a resonance form in it. Right, so that's the allyl anion. Right? And in principle, as we sort of know, neither of these is really exactly how this looks, right? It's going to be some composite of the two resonance forms. And the way to sort of think about this more generally is that you have a sort of a negative charge that is sort of shared between these. And so really what's happening here is these are sort of reflective of the two different isomers of this, but in reality, at least the way that you can sort of think about it, this is one way that you can sort of envision it, but another way to think about it is is like that, where you're basically complexing to really both carbons of this system. So again, here's, if you can see the dots, I'm sort of showing that those electrons are shared throughout that whole system, and it's really that entire al group that's in fact coordinating to this system. Okay, so back to this system. I think this is all just to sort of illustrate, you know, if this is confusing, this is all simply to illustrate one of the reasons why insertions into an al group would be favored. It's that you can insert, and then you have these resonance forms, which can certainly stabilize the system. And once you're here, now you have a sort of palladium source that is now sort of positively charged. I don't know if it's positively charged, but it's a little bit more electrophilic. And again, before we saw this idea of the metals sort of attacking in a nucleophilic fashion at the palladium. And we can do a similar mechanism here. So I'm going to abbreviate this as R minus. And what this means is we can, in essence, switch out the acetate for the carbon group. Okay? And once we've done that, now we're basically right back where we kind of were before. Right? At this step, one of the things that we can now do is what? Reductive elimination. We can bring these two together. We can form carbon-carbon bond, and we can sort of regenerate our palladium 0. Now the acetate here, where it's going to end up, you know, the counter ion, that's inevitably going to be whatever the counter ion was up here. But you can do this, and so you can use a variety of different nucleophiles, and this is one of the ones that's shown, to in essence promote this process. So again, let's just sort of rehash this one really quickly, because this is very similar mechanistically. It's probably even more similar mechanistically to the Stille and the Suzuki than the previous one that we had, right? The first step, again, is oxidative insertion. How does this one vary compared to the previous oxidative insertion? Well, it varies in the fact that now the palladium is an allylic palladium source, right? So this is one of the reasons why an allyl acetate can now insert, right? And we'll get back to this in a second because this complicates it a little bit further. But recognize that you can basically have that palladium at either carbon, which we'll get back to in a moment. Now, we're not doing necessarily a transmetallation at this step, but we can imagine a nucleophile displacing the acetate, which will then, so instead of a transmetallation, we're simply doing nucleophilic attack. And the final step, right, is going to be a reductive. Okay? So again, another way to potentially form a carbon-carbon bond. Okay? All right, so this should look very similar to Stille and Suzuki. But there is this sort of difference over here should raise questions, right? The fact that you have what's in essence two potential isomeric forms of the palladium ultimately means that where we sort of, from which one of those two we form will actually potentially lead to two very different products, right? So let me just erase this to give us more board space. But just recognize that these are the same molecule, but in principle, you could form either one of these, yeah?
According to your video, the way you showed it, you did an attack on the double bond that will knock down and kick out the palladium and then kick out the OAC stuff. But this, now that you're doing it, you're putting the palladium between the R's. Which one should we do? You did like a nucleophilic attack.
I did one before. I did a Lilith edition. I'll have to look back at that.
You understand what I'm saying?
You were
Did it
attacking
differently
here.
like this.
I'll have to look back at that.
Okay.
Okay. So I'll get back to you guys on that. But
Should we do it like this for now?
I would do it like this for now. Why did I attack there? I'll double check and see what's. This is simpler. I must have. I don't know what I read that made me think. I'll check what the book says. See, so the reason why I'm a little bit skeptical on that one there, so I'll have to read on it. The reason why I'm going this way, and I'll explain in a second. Now, I'll have to maybe look back at my notes, but the fact that we have these two isomers. Yeah, because this is exactly consistent with the still. So maybe I forgot something that I did previously that I knew. Okay, so sticking with this mechanism, and then I'll get back to you. What Jonathan is saying is that apparently in my previous video I did an addition this way. And let's to just avoid confusions. Let's assume this for now. I'll get back to you guys next class. Hopefully clarify it a little bit more because I might be missing something. But this is the way that is entirely consistent with the Suzuki and Stille. It's possible that a year ago when I taught this course, I knew something that I don't know now. I don't know. The important point here is that these are symmetric, but what if we had a system where we didn't have that same symmetry, right? What if we had a system where our acetate was non-symmetric? And in this case, we ultimately have two possible products that could form, right? So if our palladium, I guess these would be, once your palladium-2 inserts, right, we have two different palladiums. We have okay, so notice that these are two isomers of one another. So if we think about the insertion into this carbon acetate bond, we're going to get this, right? This can isomerize through that palladium al species. It can lead us to this guy over here, right? And so, I look right now. So of these two options, right? Which one of these two? And so maybe this is. I need to double check this a little more. Yeah.
With the stability of the bond count.
So that's the. See, now Jonathan's got me all flustered. No, it's fine. I'm glad you call me out on it. Maybe I looked through this too quickly this morning. So I'll have to get back to you guys on this. But let's start with this question right now. And then we'll revisit it next class, because this is a good opportunity to, I think, predict which of the products might form, and then we can sort of address it again next class. Based upon our knowledge of everything that we've known to date, if we had to predict which one of these regioisomers would form, based upon at least the mechanism that I've outlined here, which one do you guys think would form first? So the one on the right. And why would you think it would be the one on the right? It's more substituted. I'm pretty sure you get the one that's more substituted. Fine.
Wouldn't that be a problem coordinating the reductive? I mean, you bring in R minus,
Right.
right? You want them to be closer together.
Well, it doesn't matter, so I just drew on it that way. Remember, this is a dynamic system, so we can redraw it and put it in the orientation that it needs to. So are you saying that I don't know what you're saying, but
R minus takes over the oasis, so in that case, the one on the left would be better position to bond to the other?
It's going to be the same. The geometry should be roughly the same. The difference is that in one case you're going to have a more substituted double bond than the other. So I'll have to get back to you because my recollection was that it would lead to the more substituted. But now, if a year ago I taught this and I was describing...
But it doesn't matter, it's a resonance structure.
Well, no, it does matter. It matters in a major way. Because if my previous mechanism that I apparently said a year ago, then you're probably going to attack from the more substituted version, which may then lead to the less substituted alkene. So we'll have to revisit this next class because I'm, now you've got me questioning, I'm trying to keep this as similar to the Stille and Suzuki as possible. But if I mentioned sort of 1.3 or 1.4 type additions, previously allylic additions, then that changes everything. So let's revisit this one next class once I get a chance before I tell you guys stuff that's complete bogus. Let me just double check all of these things and get back to you. But again, the general idea here, let's just stick with this for now and we'll revisit it next class. If this is what you end up showing as a mechanism on the exam, that's perfectly fine if I end up putting this on here. But given the fact that I'm up in the air, I'm guessing that I'll probably stay away from this mechanism altogether on the exam. But I do still want to teach you guys what's correct, so let me revisit it and we'll come back to this next class. But again, the idea here is hopefully to see the parallels that are drawn instead of a transmetallation. At least that's kind of how I try to draw here to keep it parallel. But if it is a little bit more complex based upon addition of carbon, that would change everything. So I have to check. And a lot of these things, sometimes the mechanisms through which they can go through will be completely different based upon, say, for example, what the palladium ligands are and stuff like that. But that's really, I'll try to get you something more specific. Let's hold off on this Africa until next class. Let me make sure that I'm not teaching you guys BS. But this is all correct. Again, so what's accurate and what's potentially not accurate? I can tell you definitively that insertion and these pi-owl systems are what makes these very different. The question that's come up is apparently previously I had a different mechanism through which to get to the final product from there, and I just want to take a look at my old video, see if I was reading something previously that's different, but I'll get back to it. But ultimately, there are two regioisomers, and it's going to be worth it to make sure that we sort of know that. All right. So apologies on this. I'll clean it up and get you guys next class of this one a little bit more. Just make sure that I can clarify this for you guys. Okay, so
Just to clarify, a little cross coupling will not be on the exam.
I didn't say that. I didn't say that.
You didn't give it a name.
I just said maybe I'll be forgiving on the answers if I do. But anyway, because clearly I don't know it, or I didn't know it and now I do, or something. But whatever. Apologies. I'll get back to you guys next class. So I'll clarify that. Thank you, Jonathan, for bringing this up. I'll clarify it next class. Let me do the last cross-coupling, and then if we have time, I don't know that we're going to have much time, but I'll try to throw up one question related to some of this cross-coupling chemistry that can hopefully give you guys a sense of maybe a slightly more challenging mechanism of the extent that might be on the exam. The final one, actually I'd like to spend some time on it. Let me just show you, and I'll very briefly go after one of the final couplings that you guys need to know. And so we saw that Heck reactions, for example, can, I'll go over this one fairly quickly. But previously we saw that alkenes, when we're doing alkenes, we get this reaction that's called sort of a Heck reaction. It turns out that you can do cross couplings from alkyl halides as well from alkynes. But there's one slight difference, and in this way you'll make, so this is called a Sonogashira coupling. So this is a Sonogashira coupling. Okay? And a Sonic-Shearer coupling, it's similar, at least in principle, it's similar to the Heck reaction, at least at least conceptually, because what you're doing is, instead of taking an alkene and making a carbon-carbon bond, right, you're now taking an alkyne. And so from the standpoint of thinking about, well, what does a Heck reaction lead to, what does a Sonic-Shearer reaction lead to, you can sort of keep them together in that extent. But mechanistically, they are very, very different transformations. And you know this in large part based upon something we've seen from time to time, which is how acetylenic carbon-hydrogen bonds are much different, right, than, say, sp2 carbons or sp3 carbons, right? This is something that we've seen from first semester, right? You can deprotonate these using amides. And so as it turns out, this is this is, again, going back to the Stille and the, mechanistically this is much more similar to the Stille and the Suzuki than it is necessarily with the Heck. Now, it starts in the same way, and there's a reagent, there's a copper reagent that goes into this. But what happens is, once you get your R, okay, once you get to your palladium, sort of your oxidative insertion, as it turns out, in this case, you're not going to be using a base. You're actually going to be using a cuprate salt. And one of the things about cuprates is that you can generally take copper, I believe it's copper 1. I think you usually use copper iodide. But what happens is you actually will get an acetylenic cuprate, okay? And so your transmetallation is not actually taking place with the alkyne, but there's a previous process that takes place where the cuprate, you will end up with actually the copper-based species, okay? And you're going to do the transmetallation. Okay? And so the mechanism of this is a little bit more sort of tricky, but alkynes, you can sort of activate them with copper. You can get these copper acetylenic compounds. And then what ends up happening is you do your reductive elimination, and you generate your Sonic-Shearer products. Okay? And so... Okay, so this is another option. From a synthesis standpoint, there's certainly other ways that you can do this. For example, when I was a postdoc, sorry, not when I was a postdoc. When I was a graduate student, I was planning on using Sonic-Shearer coupling in some of my own work. But what we ended up using instead was, instead of having the cuprate, we had the alkynyl bromide, so we actually had which you can also make really easily, and then we just had the boronate. So, anyways, all right. Let me with the 10 minutes left, let me let's do a quick mechanism that might, because again, you can expect to get a mechanism, a palladium. It's not going to be overwhelming on it, but you can probably, given the fact that we're not going to get a chance to quiz you guys on this chemistry, you can probably expect to get a palladium-catalyzed cross-coupling mechanism on the exam. All right, so Let's think. So let me ask you guys a question. So actually, I'll phrase this in a slightly different way because I'm kind of thinking out loud a little bit here. But we saw yesterday with the metathesis reaction, one of the cool things about the metathesis is that, you sort of have a system where you're doing these sort of 2 + 2, retro 2 + 2s, but once you begin to get to some of these intermediates, you can oftentimes see that more complex systems can take place. So let me ask you guys this question. So I'm just going to draw something here. So if we had a sort of a Heck reaction, but this is sort of a thought experiment here to see if we could try to tie this thing together. In general, let's start here. Let's just start with a simple intramolecular Heck. So the first question is, if I were to do this transformation, I were to run this reaction with palladium, and then I'll grow it in complexity once we sort of get the first one, and I'll sort of show you guys where I was going instead of going right to the more complicated one. Let's predict what the product of this transformation might be. Okay, and so let's do that. Let's do this together. So from a mechanistic standpoint, what would be the product of this transformation? So what's the first step? So first of all, what kind of reaction am I clearly trying to get you guys at here? It's a Heck, right? If I already said that, it's clearly a Heck. And so the first step of this reaction, right, is going to be that we're going to insert into the palladium, the palladium's going to insert into the carbon-bromide bond. Okay? From here, previously we saw the Heck from an intermolecular standpoint, but sometimes when we do it in an intramolecular standpoint, simply because we're creating rings, it can be a little bit of a challenge. But what I want you guys to all try to do this on your own really quickly is we know that the alkene is going to coordinate there. And what we need to do is we need to sort of add across that alkene in some way, right? And so how might we add across that alkene? Oh, here's some ideas. So remember, this is a reminder, because I hear a lot of notebook shuffling. What we want, from a mechanistic standpoint, right, what we want is, wherever things are going to be, what we kind of want is an addition across that alkene from the carbon bromine bond. So if we're going to redraw this molecule, what do we kind of have to try to align? Again, this is similar to what we were doing with metathesis the other day, right? We wanted to sort of redraw the molecule in a way that we can have the sort of the metal carbon double bond be sort of parallel to the carbon-carbon double bond. And so in the same way, we want to do this 2 + 2, so we probably want to align this or draw this in a way where this aligns with probably this one here, right? Does everybody see that? Right? And so maybe we can count our 1, 2, 3, 4, 5, 6. Okay, so how, if that's the insertion that we're going to do, what's the size of the ring that we're going to be making?
5.
Right, the insertion that we're ultimately going to do is going to be that one there, right? So it's going to be, as Jonathan said, it's going to be a 5-member ring. So again, if you can draw from here, great, but I would probably try to redraw this part of the molecule up here. And what you can even do, potentially, is just try to bring the alkene a little bit closer to starters. We have 6, 5, 1, 2, 3, 4, 5. Okay, so that's our 3, 4. Okay. Now we can do our 2 + 2. And you notice that the bond is going to be forming between the 1 and the 5. Okay? And so if we count our bonds, we're going to have 1, 2, 3, 4, 5. And where's our 6? And our palladium, where's the 6? It's coming off carbon 5, right? Okay, so we've made a bond between carbon 1 and 5. And we're also, now the palladium is going to be between palladium 5 and 6. Okay? So now, in a Heck reaction, what's going to be the final step in the Heck reaction? Beta hydride elimination. So we're going to regenerate our alkene. Where's that hydrogen? It's at hydrogen 5. Right? And so the product, don't worry about the regenerating palladium 0 in this standpoint because we're simply asking what the product is going to be that's going to be formed. It's going to be this. Okay? All right. So what I want you guys to do is think about the fact that we still have palladium 2 as our insertion. Okay? We still have palladium 2 here. What if there was another group somewhere on there that could sort of hijack that? Right? And that's where I was initially going to go, but I thought it was way too complex. Yeah.
The product is that was forgot to go.
All right. Excuse me. Sorry. Gosh darn it. Yeah, so thank you. So we're going to generate that molecule. But what would happen, I think one of the things that's sort of interesting, and you'll see this a little bit, and so if you read through your notebook, it'll often have some examples, not your notebook, if you look through the text, I think there's a few examples where some intermediates, such as the one that you see here, can actually continue to be intercepted. And so you'll also see, in the same way that the metathesis, you'll sometimes see some cascades, sometimes on occasion, you'll also see palladium-based cascades. And that's where I was going to go initially, but then thought otherwise because of it. So, anyways, I think I'm going to call. This has been a rough day. So I think we're going to call it a day. Yeah.
Why is it a 6? What's the fun? Why doesn't it react to carbon 6?
So, good question. So the question was just asked, why is it going to react as a 5-member ring rather than a 6-member ring? That is possible. So to do the 6-membered ring, what we would need is so if it was going to go to a 6-membered ring, we basically have to go this way, right? And I'm not saying actually, you raise a good question. In general, especially with palladium catalysis, usually what you want to have is a 6-membered versus, 6-members are usually great for a lot of chemistry because 6-membered rings are stable. I'll get back to you, but I'm fairly certain when you're getting to palladium catalysts, when you're not dealing with absurd levels, it's a proximity-based issue. But I can't rule out the possibility of also getting a 6-membered ring. So, I guess to answer your question, I'm not entirely 100% sure that you wouldn't get the product arising through the 6, and so if a question like this were asked and you showed the 6 and you went through a mechanism to get the 6, I think I'd be cool with that too. So. But it's a little bit tougher to draw that way, I think, as well. All right, thanks.